Hey, it's Mr. K doing a video for AP Physics 2 and I guess Physics 1 if you guys ever get to circuits. I'm going to try to do a video on this hover cam and sound might be a little bit different, but we'll find out. Anyways, we are starting off circuits, and this is just simple circuits without a background in electrostatics. Usually we might start off with electrostatics, but this year we are starting off with circuits due to all the COVID stuff. So basic pieces of a circuit. We're doing circuit schematics. Got a voltage source here, long line, short line. Long line is usually positive, short line is usually negative. Of course, the wires come out either side, so that's what those are. The resistor is going to be something like a light bulb, anything that would impede the flow of current. And so you have little jagged lines there showing that resistance. It's going to be measured in ohms. Voltage is, of course, measured in volts. Got a switch. You can turn it on, turn it off, close it, open it as you will. It's going to stop the flow of current. The ammeter is going to measure current. Current is measured in amps or coulombs per second. And the voltmeter is going to measure volts, and that's going to be, of course, well, volts right there. The reason why there's a difference in the drawing between the ammeter and the voltmeter is that the ammeter actually needs to be placed in line so that the current moves through it, whereas the voltmeter needs to be placed in parallel to the thing that you're measuring the voltage of. So if you were to measure the voltage of a resistor, you would want to put the probes of the voltmeter on either side of that resistor in whatever circuit you have. All right, so there might be the rest of the circuit here. If we were to measure the voltage of, or potential difference of this piece, I would simply measure on either side of the piece using the probes. Okay. Last up for the just introduction part, we have series and parallel. Series means that we have things one right after the other in a circuit. It doesn't just have to be resistors, but that's what I use here for the example. And so if the current has no choice but to flow through those pieces individually, then you call that series. If the current has a choice to split off and then come back together, then we call that parallel. Not because it is drawn in parallel, but because you have these branching off of currents that will come off of a main line, branch off, and then go back and combine again. So all these pieces we will use in our circuit schematic to do simple circuits. To start off, go ahead and draw with me, if you would, a circuit, and we're going to usually try to start off with the voltage source here, and we're going to do a circuit that is, we'll do a series circuit here. And so my series circuit is going to have a couple resistors in it, a couple meaning 2, but let's go ahead and do 3. Resistor, resistor, resistor. There you go. So this battery is going to provide some push to the current. The voltage is kind of like a push to the current. It's a potential difference, much like you have a cliff here, and you have, let's say, a small rock and a larger rock. If you put the small rock and the larger rock up there, and we talked about potential energy, then we would say, yeah, definitely, because potential energy is mgh, that the larger thing, mg delta h really, it's the change in position that's available, that matters. The larger rock is going to have more potential energy than the small rock. But if we were to just talk about their potential, not their potential energy, they are both at the same gh. They're both under the same acceleration, they're both under the same height difference that they can fall, so they are both at the same potential. The whole energy thing comes in whenever you talk about the mass that it affects. Voltage is much like that, not necessarily for mass, but voltage is what we're going to use whenever we talk about the energies that could be assigned to different charges. All right, so voltage is like your potential, your GH is kind of like your voltage, whereas your charge that you place in that voltage would be much like your mass here. We'll cover that much more in detail whenever we do electrostatics. Right now, just understand that voltage is what's going to try to push that current along. Current's going to be the flow of charge as it moves around, and then resistance is what gets in the way. So here, let's say we have a battery that provides 10 volts, a cliff height of 10 volts for this charge to move through. And the charge that we're going to be talking about is the flow of positive charge. So it goes from positive to negative, even though we know now that it's actually the negative charges, the electrons, that are really the ones that are moving. Benjamin Franklin, when he first did when he first studied electricity, he had to make a choice. He said something is moving, something is going somewhere, and he just said that the positive charges were the somethings that went somewhere. And after many different experiments, they found out that what they called positive charge was actually not moving, it was the negative charge. So it's just assigning something a value, or a positive or negative, and being flipped the other way just based on convention. Don't worry about that too much. So the current here will flow out of the positive. It will want to go to the negative. The letter that we'll use for current is I, and it's going to go around in a clockwise direction, and it'll go through each of these three resistors. I'm going to go ahead and talk about the resistors in terms of, let's see, the first one we'll make it 4 ohms of resistance. I'm going to use 4 ohms of resistance here, and then we're going to use 2 ohms of resistance down here. And so if you looked at the current has to flow through all three of these resistors. There is no choice. It is a series circuit, and the total resistance that it must flow through would be 10. So if I wanted to simplify this circuit, I would simply redraw it. The same voltage applies, 10 volts, but instead of having 3 resistors, I would simply have 1. And so I have simplified the circuit to the simplest that it can get, and then I would replace those 3 with the equivalent resistance of the one 10 ohm resistor. Okay? And so in series, the way that you would find an equivalent resistance is you would simply add your resistors together. So your equivalent resistance would be equal to R1 plus R2 plus R however many there are, plus to get that total. We'll come back to this after we talk about Ohm's Law, I think. Parallel is a little bit different. If you have a circuit that has a parallel piece, that means that you will give the current an option to split off and then come back together. And the easiest way to start this is to just start by drawing a simple circuit. And so I'm going to just draw a circuit with only one resistor, and then we will expand from there. So there we go, like that. And so if we talked about this circuit being a simple circuit, we could say, yes, this thing has 10 volts to it. We could say maybe this is going to be a, oh, why not? Let's just make it the 10 ohm resistor, kind of like what we had over here when we simplified. And our voltage will push our current along, and that current will flow through the 10 ohm resistor and back down to the bottom of that battery, and then it just keeps on going, That energy that's being gained by this current is going to be dropped off in this 10 ohm resistor, and this thing's going to start getting hot. All right, it's going to be outputting a certain amount of power, a certain amount of energy per second. Remember what power is. Now, this is going to be a parallel, so we want to give that current a choice. And so let's say that this current reaches a junction point, a place where it can go either down or to the right. And it's going to choose both. Some of it's going to go down, some of it's going to go to the right. And the amount that goes down or the amount that goes to the right really depends upon the amount of resistance in the way. So if we said that this was a 10 ohm resistor as well, this current, which I'll call I1, has a choice to go down, it has a choice to go over here, and it's going to go equally. And so we can say, here's I2, and here's I3. I'm just going to say I3 because sometimes it won't be equal. But we can see, hey, I1 will split up into I2 and I3. I2 and I3 will come back together. It'll form I1 down here again. And if I wanted to, I could say, well, let's give it another choice right here. And if I do that, then now this current has a choice to split up into 3 paths. maybe I shouldn't have drawn that there, but the choice will be I2, I3 down here, and then over here we're going to have, of course, I4. Now, if I said that I4 was only 2 ohms of resistance, then you could obviously see that if the I1 had a choice to split, split, and split, it's not going to split equally. These two will be equal, but I4 is actually going to get much more current than these two would, because there's much, much less resistance. Everything comes back together as far as our currents combining are concerned, it's back to I1, but whenever they split, these two will be equal, I2 and I3. I4 will be much, much, much greater than I2 and I3 are because there is less resistance. If I wanted to make this into a simplified circuit, combine all three of these parallel resistors, not because they're drawn parallel, but because they branch off from the same thing and come back to the same thing, then there is a certain way to combine them. Because if you have resistors in parallel, each one that you have in parallel is going to lower the resistance in the way of that current. And so I'm actually going to do this in 2 steps rather than 1 for right now. So let me draw this over here. This will be our 2 ohm resistor, but what I'm going to do is I'm going to combine the 10 ohm and the 10 ohm here in the first step, and then we'll go on to a second step where we combine into only one resistor that represents all of it. So if, and this is 10 volts, if we wanted to combine this 10 ohm and 10 ohm resistor, then we need to figure out how much resistance that would be equivalent to. Well, if we have a hallway with people walking down it, if we allowed them to walk down an identical hallway right next to it, we've essentially cut that resistance in half. All right, so we added another path for those people to go. So half the amount of people would go to the other hallway, and so we can kind of think about this as combining these two to make an equivalent resistance of 5 ohms. All right, so I'm going to show you some math in a little bit, but right now just consider that. Now, if I wanted to combine these two into an equivalent resistance, consider if we only had the 2 ohm resistor there. Well, all this current would flow through the 2 ohm resistor, but let's say we opened up another path. Would that increase or decrease the resistance of the current coming out of the battery? And if we think about it, if we already have the 2 ohm path to go through, if we opened up another path, no matter how much resistance, we're still lowering the overall resistance that this current has to go through by giving it another path to go. So the combined resistance of the 5 ohm and the 2 ohm resistor will be less than the smallest one that's here. So if I were to make another equivalent circuit, this circuit will have an equivalent resistance that is less than the smallest resistor in parallel in our previous diagram. So I would expect to make a new resistance right here that would be something less than 2. And the way that we do that is in parallel, we would say that the equivalent resistance, 1 over the equivalent resistance, is equal to 1 over each individual resistor in parallel, and so on. Okay? And so just to prove the point, if we wanted to practice with these 2 resistors that we turned into the 1 5 ohm resistor, I would say 1 over the equivalent that we want is equal to 1 over 10 plus 1 over 10, and that's going to give me 2 over 10, which is going to be 1/5, and to get the REQ, that's going to be 5. And you can just reciprocal everything if you want to, but that proves that these two can be turned into an equivalent resistance of just 5 ohms. Now, if I wanted to combine the 5 and the 2, I would do the exact same thing. Let's do it down here. I would say the equivalent resistance that I wanted is equal to 1 over 5 plus 1 over 2. And we find maybe a common denominator. Let's make it 10. So I've got 2 over 10 plus 5 over 10. That's the 1/2. And that's going to give me 7/10. But I need to flip that because of the equivalent resistance value I want down there. And so my equivalent is going to be not 7 over 10, but 10 over 7. 10 over 7, let's just do this real quick, is going to be 1.42 or 1.43. And like I said earlier, the equivalent should be less than the smallest one. The equivalent is less than 2. Okay? If I want to, I can do it all in one fell swoop. In that case, I'm just going to do 1 over 10 plus 1 over 10 plus 1 over 2, 2. And then we go to the negative 1, and I get 1.43, as we just saw. So to combine things in parallel, you would do 1 over plus 1 over plus 1 over, and take the reciprocal. To combine things in series, you would add each one of these together. Now there is a reason for all that, and the reason is by going by Ohm's Law. And so this will be the important law that we will start talking about, and that is that voltage is equal to the current times the resistance. And we can use this and the fact that in series, things that are in series, you can add the voltage up. Things that are in parallel, you're going to actually want to have the same voltage of each individual thing. And I'm going to make another video for that, but we'll finish up with trying to use Ohm's Law. Using Ohm's Law, V equals IR, voltage is equal to current times resistance. Here for this first one, here's the voltage, the potential difference to start that the current needs to go through. So I'm going to say that's 10. The current is kind of what I want, and the resistance is just going to be 10 as well. So that means that the current is going to be 1 ampere in this case. 1 ampere that flows through is going to go through each one of these. I can apply Ohm's Law, V equals IR, to each one of these, which means that the voltage is equal to the current times the resistance. So I have 4 volts here, and it's going to use up 4 volts, so really it's negative 4. If I have 1 amp here, it's going to be 4 again, 4 volts. And if I have 1 amp through the bottom, it's going to be 2 volts. And the total voltage should be equivalent to the voltage provided by the battery. Now that's not going to help you out very much, but it kind of does prove a slight point. Will be a little bit better later on. Here, if I wanted to say the voltage is 10 volts, if I wanted to find the current out of the battery, I would do V equals IR. 10 V equals I straight out of the battery. R is 1.43 total. I'm going to say 10 divided by 1.43 gives me about 7 for our current. 7 amperes for the current. And double check, IR should equal 10. That's just the math backwards. Now, what I mean by the voltage is carried over or copied over is that everything in parallel should have the exact same voltage. So the voltage here should be the same as the voltage there, should be the same as the voltage there. All 3 of these branches will have the exact same voltage because the energy that is involved with the current starts off as the same thing. We're going through these different paths. It's just less amount of electrons driving it through. So I can start off at the top, I can improve it by the bottom, and we're going to do both. I know this is going to run a little bit long, but 10 volts, 10 volts, 10 volts. All these are in parallel. They should have the exact same voltage as the thing that they're in parallel with. And so the other way to do it is you can look at a closed loop and say that for a closed loop the total voltage should be 0. And so we have 10 volts given, 10 volts taken away. Here's another closed loop. 10 volts given, 10 volts taken away. Here's another closed loop, the outside loop. 10 volts given, 10 volts taken away. So I can say, all right, if V equals IR, that means that V over R is equal to I. So if I could just take the voltage divided by the resistance, and I get the current. Voltage divided by the resistance, the current is going to be 1 ampere. 1 ampere again. And then the voltage divided by the resistance, 10 divided by 2 is going to be 5 amperes. And if you notice, 5, 1, 1, that's a total of 7. That's 7 amps right there. So the math works out. I'm not going to do this last one, but the math does work out. We're going to cover this a lot more, but this video is getting a bit long, so I'm going to stop it right here.